It rests quietly on the ground, exposed to the sun, wind, and rain, seemingly motionless and entirely silent. Because our human lifespans are so brief, we perceive the ground beneath our feet as a permanent, unchanging fixture. But long before we arrived, Earth was engulfed in a continuous, dynamic state of planetary change. Entire oceans expanded and vanished. Massive, ancient volcanoes violently erupted, and rivers moved staggering sediment across slowly shifting continental plates. To a geologist, a rock is a natural time capsule that records these massive events. Analyzing these mineral structures provides the means to reconstruct environments that vanished millions of years ago. The record often begins in water, where mud, sand, and other loose sediments gradually gather over vast periods of time. As these materials pile up, the crushing weight of the layers above generates extreme pressure, transforming the loose debris into solid strata of rock. This cross-section shows how, when left undisturbed, the oldest layers remain at the bottom, while the youngest settle on top, much like the pages of a history book. Each stratum preserves distinct evidence of the specific environment that existed when it formed. Tucked within these environmental signatures are fragments of ancient ecosystems, the biological remains we call fossils. These biological markers include subtle traces of life, such as ancient footprints, delicate leaf impressions, or shells of tiny marine creatures. Discovering one of those marine shells high above modern sea level provides physical evidence that a dry landscape was once covered by an ocean, allowing us to map ecosystems that have completely disappeared. Determining what happened is only one part of the investigation. Scientists must also calculate exactly when it happened. To find the precise age of a rock, researchers rely on a process known as radiometric dating. Certain minerals contain radioactive elements that slowly change into stable elements at a predictable rate. By measuring the proportion of original radioactive elements against newly formed ones, scientists can calculate a precise age, placing the mineral on a timeline stretching back billions of years. This chemical analysis allows us to replace estimates based on visual appearance with a mathematically precise chronology of geological events. Beyond their age and fossil contents, the physical signatures of the minerals themselves carry information about ancient climates. A porous texture might point toward ancient volcanic activity, while specific mineral grains indicate the shifting dunes of a desert. These physical signatures are often locked away deep underground, requiring massive planetary movements to bring them to the surface. Driven by tectonic forces, massive sections of Earth's rocky crust are slowly thrust upward, creating mountain ranges that eventually reach thousands of feet. Once exposed, these towering peaks are relentlessly battered by punishing wind, rain, and expanding ice over enormous geological timescales. This constant weathering strips away the outer material, exposing the deeply buried, ancient layers of rock to the surface. A mountain serves as a continuously opening geological archive, exposing deep planetary history along its rocky slopes. Reconstructing the past requires synthesizing every piece of evidence, age, environment, fossils, and minerals, into a cohesive narrative. And that planetary narrative is far from complete. Earth is still actively writing its story. Today, rivers continue to transport millions of tons of sediment, while active volcanoes constantly extrude fresh lava to form brand new rock. Deep beneath us, tectonic movements and earthquakes are actively fracturing and moving the crust. The very geological formations taking shape right now will eventually serve as the evidence for future observers studying our current era. It brings us back to the seemingly silent object resting quietly on the ground. A stone is a surviving page from Earth's ancient history, providing context for the ground we walk on.